Welcome to the video lesson for section 1.4, shifting, reflecting, and stretching. We're going to talk about how to do that to several types of functions and then what the resulting graph might look like. Let's get started. Before we can talk about shifting, reflecting, and stretching, we need to identify the idea of a parent function. So the most basic parent function is the heart of the function, which gives it its defining characteristics. We have several that you probably are familiar with. The first one here we have is f of x equals x squared, but there are several more. All right, we also have f of x equal just plain old ordinary x. We have f of x is going to equal x cubed, and we can extend this pattern for different powers, so let's look at different types of functions. We also have f of x is going to equal the square root of x, or f of x would equal the absolute value of x. So these are all different functions you've seen throughout math, and we're going to talk about how to, again, shift, reflect, and stretch these parent functions, and the result would be moving this or changing it based off of what we're doing to it. All right, the first transformation we're going to talk about are vertical shifts. The vertical shift is going to shift the graph up or down, and to do that, we're going to add a number to the function. So if I want to shift the unit up c units, we can see I have a plus c over here. Let's take a look at what that might look like with a function. Let's say that we have f of x is equal to the absolute value of x, and I want to move that up 3 units. Well, our new function, h of x, would be the absolute value of x plus 3. So we can see what we have is the original function, f of x, and then we're adding c units to it. If I wanted to shift it down c units, well, I would just be subtracting c. So let's take that original same function and let's move it down 3 units. I'm going to call this g of x. And if I'm going to move it down 3 units, then we have the absolute value of x minus 3. So again, this number on the outside is going to tell us if we're moving down or if we're moving up. That's what our vertical shifts are doing. All right, so here we can see some visual vertical shifts. Our parent function is x squared plus 1. And what I want to note here is the parent function is just the starting function for the problem itself. If I want to take this and move it up 2 units, I'm going to be adding 2 to my function. So I have f of x plus 2, which results in x squared plus 3. You can see my green function is visually 2 units higher. Our original function here, f of x, was the blue one. If I wanted to move it 2 units down, I would then be subtracting 2. So I have f of x minus 2. Positive 1 minus 2 is going to end up being x squared minus 1. And we can see visually our red graph has been moved down 2 units. So once again, our vertical shifts are either up or down, and we accomplish them by adding and subtracting something to the function itself. For our horizontal shifts, this one is a little bit different. It is going to be moving horizontally, meaning left or right, but we actually end up doing the opposite of what you might think. So if I want to move something to the right, then I have x minus c. So I'm subtracting something to move something to the right. All right, let's kind of think about why that makes sense. Let's say that I had an expression like x minus 3 equals 0, and I solve that expression, I end up getting x equals a positive 3. So if I start off by subtracting something and I solve it, I get a positive value, which is why we result in this shift to the right. If I instead want to move something to the left, then I'm going to be adding. Let's look at an expression here. Let's say that we had x plus 5 equals 0. If I were to solve that, then I end up getting x equals negative 5, which again justifies our shift to the left. One thing to note here is our horizontal shifts is applied directly to the x value, so it's going to be in parentheses with our x value wherever you see that. Whereas your vertical shift was added to the function itself, so it ended up being on the outside. So again, horizontal shifts are in the inside of the parentheses attached to the x, whereas your vertical shifts would be on the outside. Okay, if we take a look at what this would look like visually, if I want to move something 2 units to the right, we can see I would be subtracting that from my function. So I'd start with x plus 1. If I subtract 2 from that, I end up with x minus 1, and we can see the red function again has been moved to the right when we compare it back to our blue function. If I wanted to go 2 units to the left, I'm going to be adding those 2 units. So if I start off with x plus 1 and I added 2, I would see x plus 3. And again, we can see that was visually moved to the left. So by adding, we went left, and then by subtracting, we went to the right. All right, for our next transformation, we're going to talk about reflections. And we have 2 types of reflections. We can reflect something across the x-axis, which means we're going to see the mirror image as we reflect it down. And the way that we're going to do that is if we start off with the function f of x, we're going to make the entire function negative. So you're going to see, again, instead of a positive function, we have a negative function, and that will reflect it down. And it accomplishes it by changing all of the y values to be their opposite signs. If we look at our example, we have positive absolute value of x plus 1. So I want to reflect that down across the x-axis, I now have a negative absolute value. We have another example over here. If I had a positive x squared, to reflect that across the x-axis, I would put a negative in front and make it a negative x squared. Now I want to kind of clarify here that negative x squared really should look more like this. So we know we're making the entire function negative, not just our x value. If we wanted to instead reflect something across the y-axis, what we're going to be doing is we're going to replace the x with a negative x, and we're going to end up seeing a mirror image across the y-axis. So instead of a positive x, we're going to replace that with a negative x. And this is different than our example from the last slide. Notice that we have x squared, and then we have in parentheses negative x squared, whereas if we reflect it across the x-axis, that negative would be on the outside. So again, if we want to reflect it across the y-axis, we replace x with a negative x. If you want to replace it across the x-axis, you make the entire function negative. For our non-rigid transformations, we're either going to be shrinking or stretching our function. And we can do it two different ways, vertically or horizontally. To begin with, if we multiply by a number that is larger than 1, we're going to have a vertical stretch, which means the whole graph is going to be a lot taller. An example of that we can see we have 3 times f of x, where again we're going to be multiplying the whole function, so we have 3 on the outside times our function f of x. If instead we multiply by a number that's going to be between -1 and +1, that's going to be a shrink or a vertical compression of the graph. And we can see on the outside again we have a 1/3 times our f of x. So again, just to recap, if you multiply your whole function by a number larger than 1, it's going to be a vertical stretch, the function will be taller. If you multiply by a number between -1 and +1, you're going to have a vertical shrink or a vertical compression of the graph, and it's going to be shorter. In addition to our vertical non-rigid transformations, we have horizontal non-rigid transformations as well. To begin with, if you multiply by a number that is larger than 1, we're going to have a horizontal shrink. And we're going to be multiplying our x value by something larger than 1. If you look at our notation here, we have f of 3 of x. So notice that the actual x value is what is being multiplied by our constant. And by multiplying by a number larger than 1, we're going to be doing things a lot more quickly, which is why we have a horizontal shrink of our function. If we instead multiply by something between -1 and +1, then we're going to have a horizontal stretch, and we can see we have f of 1/3. And the reason why we have a horizontal stretch is because it's taking a lot longer for our function to do things, because we're cutting all of the x values by 1/3. And so the whole thing is going to be horizontally stretched out and much, much longer. So here we can see visually something being horizontally stretched or shrunk. Notice that if we multiply by a number that is bigger than 1, for our blue function here, we can see it is definitely going to be horizontally shrunk or compressed because it is narrower than our green function. If instead we multiplied x by something that is going to be between -1 and +1, then we can see it has been visually stretched and it is much more wider than our green function. So again, just to reiterate, if we multiply by something that is bigger than 1, then we're going to be horizontally shrinking it. If instead we multiply by something that is between -1 and 1, then we are horizontally stretching it. Alright, for our function here, we're going to describe all the transformations. The first thing we want to try and do is identify the most basic function here, which we'll call the parent function. And for that, I'm going to say would be g of x is equal to x to the 4th power. So every number added to this function is going to do some kind of change. And we're going to do it one at a time. We have a -3 that's going to do a change. We have a -5, and we have a +7. And we'll just go left to right. So for the -3, that's going to accomplish 2 things. The negative part is going to flip this over the x-axis or reflect it. And then that 3, since we're multiplying the function by 3, we're going to have a vertical stretch by a factor of 3. Okay, for the -5, that's going to be our horizontal shift. And we just want to say which way it's going to go. Since it's -5, we're going to end up going to the right 5. And then for our +7, that's going to be your vertical shift. Since it's a +7, we're going to be going up 7. All right, here for our next function, we have s of f. And for the parent function, again, it's the most basic, which would be the absolute value of f. What I want you guys to do now is go ahead and try to correctly identify all of the transformations to this graph. All right, so we have a few numbers to consider here. We have the 4, we have the -2/3, and we have the +3. Let's go ahead and just do this from left to right. So for our 4, that's a number that's detached from the function itself. So that's going to take this whole function and move it up 4. For the -2/3, that's going to do two things again. So the negative sign is going to reflect it across the x-axis. So we'll just say across the x-axis. And it's also going to have a vertical shrink here. And the vertical shrink is a factor of 2/3. And then last but not least, we have a +3. Now because it's a +3, we know it's going to be moving to the left 3. And those are all of your transformations. All right, so for example, now we have a parent function of x squared. We want to do a few things. We want to shift it up 5, left 7, and it's going to be narrower by a factor of 3, which translates into a horizontal shrink. So we're going to start with our function. We know we have x. We know it's squared. We've got some numbers to fill in. We're just going to go again from left to right. Because it's going to go up 5, I know that's a +5 to the function itself. It's going to go left 7, which means I'm going to be adding 7 to the function. And it's narrower by a factor of 3, which I said is going to be a horizontal compression. So we're going to be multiplying this by 3. And now we have our function. All right, for our next example, our parent function is going to be x + 1 squared. We're going to shift that down 2, left 4, and wider. So this is going to be a horizontal stretch. Again, a horizontal stretch by a factor of 5. So go ahead and select which one you think is the correct answer. Okay, so let's go ahead and start with our base function. So we have x + 1. And leave some space in here so we can add in our transformations here. Going from left to right, we are starting with down 2. So if we're going to go down 2, that's going to be subtracted from our function on the outside. Going left 4, we're going to be adding 4 on the inside. And last but not least, we're going to be wider by a factor of 5. So we're going to have a 1/5 in front of our x. If we go ahead and simplify this whole thing, then we get 1/5 x plus 5 squared minus 2. All right, just to summarize, we have an equation of y equals a times x minus h to the nth plus k, or if this was a square root or absolute value bars, it'd be the same basic pattern. A is going to determine which way the graph opens. If A is positive, it's going to open up. If A is negative, it's going to open down. A is also going to determine if you have a vertical stretch or a vertical shrink. If A is greater than 1, it is a vertical stretch. If A is between -1 and 1, it's going to be a vertical shrink. H is going to affect which way a graph moves horizontally, either left or right. If H is positive, we're going to go left. If H is negative, we go to the right. So basically, it's going to do the opposite of whatever its sign is. K is going to tell us if things are going to go or move up or down physically. If we have K greater than 0, it's going to go up. If we have K less than 0, it's going to go down. All right, that concludes our lesson. Go ahead and start the homework. Good luck.